This is an RTLSDR, a small cheap USB device that allows you to tap into the radio signals that surround us at all times. Almost every wireless device you encounter use radio signals to work. But radio is also used for communication, satellites, and even mysterious shortwave signals that travel around the world. What if you could see, hear, and decode these invisible radio waves? The cheapest way of doing so is by getting an RTLSDR. But what is this small USB device, and how does it work? About a decade ago, some clever people discovered that an unassuming looking, cheap and mass-produced USB receiver for digital broadcast TV had inside it a chip called RTL2832U, which turned out to be much more capable than it needed to. With a custom driver, the very cheap and readily available USB device turned into a fully fledged SDR receiver, capable of receiving frequencies up to around 2 GHz. And the RTLSDR was born. Now there are quite a few different RTLSDR devices out there, and plenty of different manufacturers putting those chips on boards with varying frequency ranges, quality, stability, noise, and other extra bits. However, I'd recommend the one from RTLSDR blog, which implements useful features such as a temperature-compensated oscillator for better frequency stability, a powered bias tee for powering amplifiers and active antennas through the antenna port, and this latest version has built-in HF up conversion for much improved HF reception. But let's back up a bit. What is an SDR receiver actually? SDR is short for software-defined radio. Traditional radios have circuits built specifically for the modulations, filters and tuning that the radio needs to perform. Those physical components modify analog oscillations in a series of carefully organized circuits and relays, which end up at a speaker. If you wanted a different modulation or filter width, you'd have to design and implement it physically. But with an SDR radio you can simply change the programming, and any filter and modulation type is but a mouse click away, and at a much higher precision than what was possible with analog components. Additionally, traditional radios are mostly limited to monitoring a single frequency, but with an SDR we can monitor a wide frequency spectrum and quickly see where the signals are transmitted, instead of having to tune backwards and forwards in hopes of passing by just as a signal is transmitted. Today we have a wide variety of SDRs available, and some can even transmit. However, none are as inexpensive as the RTLSDR, so this is a great starting point, even if it is only a receiver. All SDRs require software, and there are plenty of different applications, all with their own quirks and useful differences. Let's take a look at some of the different applications and their uses. There are several variants of the general purpose receiving type software available, such as SDR Sharp, SDR++, HDSDR, and the relatively recent SDR console. These types of applications let you browse the frequency spectrum, visualize the signals, tune into them, and listen to regular FM, AM, and SSB broadcasts. RTLSDR can see about 2.5 MHz of the spectrum simultaneously. Up top it is visualized as a spectrum, and below we have the waterfall, showing us signals over time, giving us an indication of what frequencies we could tune to. We need to know a bit about how radio frequencies work in order to know how to operate the software and what antennas to use. Radio frequencies are split into ranges. For instance, the range known as VHF, or very high frequency, covers the frequencies from 30 to 300 MHz, and the range known as UHF, or ultra high frequency, covers the frequencies from 300 to 3000 MHz. In these ranges you will find stuff like broadcast FM stations, aeroplane communications, local commercial communication, or even satellite signals. All those signals need to be relatively in line of sight of your antenna, so having your antenna up high and outside, clear of surrounding walls, buildings, hills or trees, will improve your receiving range and signal strength. This also means that your receiving range is limited by how far your antenna can see, and that signals beyond the curvature of Earth are unreachable unless bounced off objects in space or retransmitted by satellites. The physical size of the invisible radio waves traveling through the air that we're trying to detect is linked to the frequency of the signal. The higher the frequency, the smaller the wavelength. If you're using a dipole antenna, it needs to be roughly half the length of the signal you're trying to receive to get the best signal strength. A longer antenna isn't necessarily better, although some specific antenna designs will increase the gain of the antenna in one or more directions. The best antenna is the proper length for the signal that you're trying to receive. For instance, the wavelength of 433 MHz is about 70 centimeters, but the wavelength of 144 MHz is about 2 meters. As we go lower in frequency, the wavelength and thus the appropriate antenna length increases significantly. The frequency range of 3 to 30 MHz is known as HF, or high frequency, but you might also know it as shortwave. Those names are a bit confusing nowadays, because compared with the more common VHF and UHF, HF is actually quite low in frequency and quite long in wavelength, the lower parts reaching lengths of as long as 80 meters. Something is a bit weird about the HF frequency range though. These radio signals will bounce off the ionosphere, a layer high in the atmosphere, and reflect down to Earth again, sometimes several times over, possibly reaching all around our Earth. So you can receive HF signals much farther than VHF and UHF. In this frequency range you can find all sorts of signals, such as broadcast AM stations from countries far away, marine, aircraft and military communications, and straight up mysterious number stations and odd bleeping and buzzing signals. You will need much longer antennas for HF reception though, but they can be as simple as a long piece of wire. Also be aware that HF is much more prone to noise coming from local electronic equipment, and that receiving weak HF signals is much easier when being far from civilization. Also, the propagation changes in relation to time of day, time of year, and even the current solar cycle and solar winds, which all affect how and what frequencies the ionosphere can reflect. In all frequency ranges you will come across licensed amateur radio enthusiasts, also known as hams, who have their own dedicated sections of bands where they carry out experiments and communicate with each other, using a variety of different analog and digital modulations or even Morse code. To listen to the different signals, you need to set your software to the correct modulation type. Modulation is how the audio is put into the radio signal, either by FM, which modulates the frequency of the carrier, or AM, which modulates the amplitude of the carrier. There's a third modulation type called SSB, and unlike FM and AM, it doesn't have a carrier, so there's only a signal as long as there's audio being transmitted, and you cannot necessarily hear when the other part stops transmitting. SSB is either transmitted on the upper sideband, known as USB, or lower sideband, known as LSB. On VHF, UHF you will mostly find FM signals, although airplanes use AM. On HF you will mostly find SSB signals, and most of these will be USB. If a signal sounds weird, try a different modulation type. Commercial HF radio stations use AM. This is where the common misnomer comes from of describing HF as the AM band and VHF as the FM band. You will also find digital signals which will sound like either bleeps or noise, and some will be at a wider than common modulation width. You can adjust the modulation width, although mostly the default width will be correct. If you pick the CW modulation, which is used for Morse code, you get a very narrow modulation width, allowing you to focus in on a single Morse code signal. Tuning around, listening to and discovering new signals is a lot of fun. But let's jump ahead to another piece of software which will allow us to decode some of these signals that we're hearing. SDR Angel might look a bit intimidating and confusing at first, but it is a very powerful and useful piece of software. It is not for browsing around the bands. When you open this application, you know what frequency you're looking for and what signal you want to decode, because that's what SDR Angel does. It decodes signals, and it supports using RTLSDR directly. Let us for instance try and decode airplane location ADSB packets. We set the frequency to 1090 MHz, add the ADSB demodulator, and now planes within receiving distance will start popping up on our map as we pick up and decode the location data they're transmitting on the frequency. Similarly, we can decode amateur radio location data packets, known as APRS, and display the results on a map. And we can also decode AIS packets, transmitted from local ships and boats, displaying their position and movement on a map. SDR Angel also includes demodulators for lots of other interesting stuff, such as RTTY, FT8, pages, packet data, broadcast digital radio, weather balloons, and much more. There are also other dedicated pieces of software for RTL-SDR decoding purposes, such as Dump 1090, which decodes ADSB packets and puts them on a local web page map, or RTL433, which can decode lots of the packets sent on the ISL bands, which is commonly used by weather stations, temperature sensors, tire pressure sensors, and other wireless devices. Decoding radio signals has been a thing even before SDR radios came about. Back then we would use a dedicated radio and then plug in the audio into the computer. Because of this, there are plenty of applications that can't use RTLSDR directly, but expect an audio input. We can still provide this by digitally piping the audio output of our general-purpose SDR receiving software into the other applications. This opens up a whole lot of possibilities, such as a multitude of different text and data modes, HF weather facts, SSTV images, or even decoding weather satellite imagery. If you combine the RTLSDR with a Raspberry Pi, you can turn it into a remotely controlled radio receiver. There is a very impressive piece of software called OpenWebRX that provides a web interface for listening to and even decoding signals live. This way you can place your RTLSDR in a suitable noise-free location far from other electronics and get a nice clean reception provided it has internet access. There are far too many applications that can be used with RTLSDR for me to mention here, so I'm going to leave you with a couple of tips and tricks for getting started with RTLSDR. Number 1. Use an appropriate antenna for what you're trying to listen to, and place it outside or at least near a window. RTLSDR Block sells a handy suction cup dipole with telescopic whips that can be adjusted in length. Use an antenna length calculator to find the suitable length for the frequency you're trying to listen to. For HF, I recommend using longer pieces of wire. You can for instance hang it from a tree. And if you don't have space for a full-size antenna, just have it be as long as the conditions allow for, or bend it to fit around a garden for instance. Experimenting with building and mounting antennas to increase efficiency is a big part of the radio hobby. Number 2. Move your receiver and antenna far away from possible noise sources. Any electronic device will emit some amount of electromagnetic noise. Lots of devices will emit lots of noise, some more than others. This includes your computer but also power adapters, solar cell inverters, and some LED lights. If you're experiencing a lot of noise, try turning off devices in your house one by one until the noise goes away. You can even try using a laptop on battery power and move around to determine the location of the noise. Number 3. If you have transmitting radios, don't use them in close proximity of your SDR receiver or any radio receiver, as it might overload and damage it. Move away at least a couple of meters and turn down the power output.
Even then you will probably see that the signal can look distorted and repeated across the spectrum due to overloading the receiver.
Number 4. Be mindful of the gain setting. By default, the SDR application that you're using might have set the gain of the receiver to 0. This will severely limit what you'll be able to receive, if anything. You can adjust the gain manually until the signal strength seems appropriate, or you can try to use the auto gain control, although it will sometimes gain the signal too much and cause distortion or ghost signals to pop up in places they shouldn't be. And finally, number 5. Be mindful of your antenna's orientation. Most radio transmitters have their antennas oriented vertically, and this means that your receiving antenna needs to be oriented vertically as well. If your antenna is incorrectly oriented, by for instance 90 degrees, it will degrade the signal strength significantly at more than 20 dB. This is less important on the HF bands, as the polarisation is randomized by the reflections of the ionosphere. Having access to what an RTLSDR can do would have been prohibitively expensive in the past. It is an extremely useful and powerful tool, especially at such a low cost, and I would recommend it if you are in any way interested in wireless communications. I hope I've given you a small insight into what RTLSDR is all about.